Welcome to this presentation on transition metals. Transition metals are elements found in the D block of the periodic table. They are known for their colored compounds, variable oxidation states, and ability to act as catalysts. Definition and position in the periodic table, electronic configuration of transition metals. Transition metals are defined as elements that form at least one stable ion with a partially filled D subshell. This definition is crucial, as it explains why some elements found in the D block, such as zinc, are not classified as transition metals. Zinc forms only Zn² ions with a full D subshell, 3D to the power of 1, meaning it lacks the characteristic chemistry associated with transition metals. Transition metals are located in the center of the periodic table, between the S block and P block elements, spanning groups 3 to 12. Their position reflects their unique electronic structure, where electrons are added to the D subshell after the outer S subshell has been filled. This electronic arrangement underpins many of their key properties, including variable oxidation states, formation of colored compounds, and catalytic activity. Transition metals follow the general filling order where the 4s orbital fills before the 3d orbital. However, when ions are formed, electrons are lost from the 4s orbital first. For example, iron has the electronic configuration R3d4s², but Fe² is R3d and Fe³ is R3d. This behavior explains why transition metals can exhibit variable oxidation states, as both the S and D electrons can be involved in bonding. The small energy difference between the 4s and 3d orbitals means that removing different numbers of electrons requires similar amounts of energy, enabling multiple stable oxidation states. Physical properties, density, melting point, and strength. Transition metals have high densities, high melting points, and high tensile strength. These properties arise from the strong metallic bonding present in transition metals, which involves delocalized electrons from both the outer s orbitals and the d orbitals. The increased number of delocalized electrons strengthens the electrostatic attraction between the positive metal ions and the electron cloud, resulting in stronger bonds. For example, iron and copper are much denser and have significantly higher melting points than sodium or magnesium. Origins and chemical significance of variable oxidation states. Transition metals form compounds in different oxidation states due to their partially filled D subshells. The small energy difference between the 4s and 3d orbitals allows electrons from both subshells to participate in bonding, leading to a variety of oxidation numbers. For example, vanadium commonly forms +2, +3, +4, and +5 oxidation states, each associated with compounds of different colors. This variability is highly significant in redox chemistry, catalysis, and complex formation. Formation of complex ions and the role of ligands, coordination number, and shapes of complexes. Complex ions are formed when a central metal ion is surrounded by molecules or ions known as ligands. Ligands donate a lone pair of electrons to the metal ion, forming a coordinate, dative covalent, bond. Common ligands include water, ammonia, and chloride ions. The ability of transition metals to form complex ions is due to their high charge density and availability of empty orbitals to accept electron pairs. For example, the hexaaquacopper 2 ion CuHO² is formed when copper 2 ions dissolve in water, producing a characteristic blue solution. The coordination number of a complex ion refers to the number of coordinate bonds formed between the central metal ion and surrounding ligands. This number determines the overall shape of the complex. Common coordination numbers include 6, leading to octahedral shapes, and 4, which may result in tetrahedral or square planar geometries depending on the metal and ligands involved. For example, CuHO² is octahedral, while CuCl² is tetrahedral. Origin of color in transition metal compounds. The characteristic colors of transition metal compounds arise from electronic transitions within the D subshell. In a complex ion, the approach of ligands causes the degenerate d orbitals to split into two energy levels. When visible light is absorbed, an electron can be promoted from a lower energy d orbital to a higher energy one. The color observed is the complementary color to the light absorbed. The exact energy gap, known as E, depends on factors such as the metal ion, its oxidation state, and the nature of the ligands. For example, replacing water ligands with ammonia in a copper 2 complex leads to a deeper blue color due to increased splitting. Mechanisms and observations of ligand exchange. Ligand substitution reactions involve the replacement of one ligand in a complex ion with another, which occur in aqueous solution and are accompanied by clear color changes, making them useful in both practical work and examination questions. For example, adding concentrated hydrochloric acid to a blue solution of CuHO squared results in the formation of the yellow-green CuCl squared complex. Transition metals as oxidizing and reducing agents. Transition metals play a central role in redox chemistry due to their variable oxidation states, allowing them to act as both oxidizing and reducing agents. For example, Fe² ions can be oxidized to Fe³ by oxygen, while Fe³ ions can be reduced back to Fe² by zinc. These processes are fundamental to applications such as corrosion, electrochemical cells, and industrial synthesis. Homogeneous and heterogeneous catalysis. Transition metals and their compounds are used as catalysts due to their ability to change oxidation state and form intermediate complexes with reactants. In heterogeneous catalysis, such as the use of iron in the Haber process, reactants adsorb onto the metal surface, weakening bonds and lowering activation energy. In homogeneous catalysis, such as the use of cobalt complexes in solution, intermediate species form during the reaction pathway. Hydroxide precipitates and qualitative analysis. When hydroxide ions are added to solutions containing transition metal ions, insoluble metal hydroxides often form, each with a characteristic color. For example, adding sodium hydroxide to a copper solution produces a blue precipitate of CuOH, while iron ions form a brown precipitate of FeOH. Summary, exam skills, and common pitfalls. Students should practice writing clear, concise explanations that link electronic structure to observed properties such as color, magnetism, and catalytic behavior. Common pitfalls include incorrect electronic configurations, poor use of oxidation numbers, and vague descriptions of observations. Transition metals are important because of their variable oxidation states, colored complexes, ligand chemistry, and catalytic properties. These features make them useful in industry and everyday life. Thank you for watching.